I hope you did your test 1 well. Today we begin Unit 2, which is the study of thermodynamics. What does thermodynamics deal with? Thermodynamics deals with the study of heat and temperature. So, we begin by defining heat. Do you know what heat is? Well, heat is a form of energy. Well, you know there are many forms of energy. Now, heat is a form of energy, and when you supply heat to an object, what happens? The internal energy of that object will increase. What is the meaning of internal energy of an object? Internal energy of an object is made up of potential and kinetic energies of the atoms and molecules that make up the object. Now, you know, kinetic energy is associated with the speed of motion. And you know, when you supply heat to an object, the molecules will pick up speed. Is that right? Okay. How about potential energy? Potential energy is associated with relative positions of atoms and molecules. Tell me, when does this ball has maximum potential energy? You know that in order to move this ball away from the surface of the earth, I have to do work. So this ball has maximum potential energy with respect to the earth when it is very far from the earth. So, if you have a system of objects, when is their potential energy maximum? Their potential energy is maximum when they are much farther apart. When they are closer together, their potential energy is the minimum. In a solid, for example, the molecules are very closely packed. That means they are held by intermolecular forces very strongly. In such a case, we say the potential energy is the least. In order to separate them, you need to do work. And this work can be done by supplying heat. So supplying heat can increase the potential energy of atoms and molecules. It can also increase the kinetic energy of atoms and molecules. In this unit, we will study about these two phenomena. Well, so let's talk about temperature and gas laws. We have a fairly good idea on what heat is. We said heat is a form of energy, and when heat is supplied to an object, it increases the internal energy of the object. We also said internal energy of an object is made up of kinetic and potential energy of its atoms and molecules. Now, atoms and molecules have kinetic energy because of their vibrational, rotational, and translational motions. You see, all kinds of motions atoms and molecules can have. And when any of these types of motion change, the kinetic energy change. And potential energy of atoms and molecules are associated with their relative states or positions. When you want to separate atoms and molecules, their potential energy increases. You know, if you want to crack a nut, what do? You place the nut on a surface and bang it. Is that right? Now, what are you actually doing? You are supplying energy so as to break the nut into pieces. And what you see are the pieces flying away from each other. The amount of energy you supplied increases the potential energy of the system in taking them apart. Now, potential energy of a system is greater when the objects are farther apart, and the potential energy is minimum when they are closer together. All right, what is temperature? Very often these concepts are confused by students. What is the difference between temperature and heat? Can you give me a satisfactory explanation on the difference between temperature and heat? Well, when heat energy is supplied to an object, its temperature rises. But the question is, will it happen all the time? We will answer that question as we move on. Now, the rise in temperature is purely due to the increase in the translational kinetic energy of the molecules of the object. In other words, the temperature increase is purely due to the increase or decrease in kinetic energy. If a potential energy is not registered as an increase or decrease in temperature. So temperature is affected only by the translational kinetic energy. That means when the kinetic energy is maximum, the temperature will be maximum. When the kinetic energy is minimum, the temperature will also be minimum. All right? Here I have an illustration of molecular motion. You can see the lower temperature corresponds to rather very slow motion of molecules. You can actually see molecules in a gas move at random. They hit against each other, and the molecular speeds represents the temperature. If you increase the temperature, the molecular speeds also will increase. Now, this is a slightly higher temperature. You can see the molecular speeds are greater in this case. So temperature is purely determined by molecular speed. In order to distinguish between temperature and heat, let us consider two different quantities of water, one in a small beaker and another in a big beaker. A large quantity of water and a small quantity of water are supplied heat at the same rate. Both receive heat at the same rate. Tell me, which of these will register a higher temperature? Well, I know most of you will tell me that this will register a higher temperature. Why? What is the reason? The same amount of energy is shared among less number of molecules here than in the large container. That means the share of energy per molecule is much greater in the smaller beaker. Is that right? Each molecule in the smaller beaker will now have much greater kinetic energy than the energy in the bigger beaker. So the larger quantity will have a smaller increase in temperature, while the smaller quantity will have a larger increase in temperature. Why? Because the average energy received by molecules in the smaller beaker will be greater. The energy per molecule will be greater. Can we use that to define temperature? Look at the way I have defined temperature. Temperature of an object is proportional to the average kinetic energy of its molecules. So if a substance, the molecules of a substance has average kinetic energy greater than the molecules of another substance, we would say the temperature of the first substance is greater. Temperature is proportional to the average kinetic energy of the molecules of that substance. Now look at this. I have two substances that have the same average kinetic energy but different amounts of potential energy. That means the internal energy, the total internal energy of the second object is much, much greater than the total internal energy of the first object. But because the average kinetic energy is the same in both cases. They are both of the same temperature. Temperature is determined by the average kinetic energy of the molecules. In other words, it depends on the square of the velocity. How do we measure temperature? Well, of course, we use a thermometer. Now, in order to measure temperature, we make use of properties of materials that change with temperature. Can you tell me some of the properties of materials that change with temperature? When you heat an object, what are some of the properties that will change? If I heat this metal rod, its length will increase. If you heat a given quantity of water, its volume will increase. Have you ever seen that happen? If you fill a container up to the brim and heat it, as it begins to warm up, as it begins to heat, the water will expand and overflow. Try it if you don't believe me. So heating a substance will increase its volume, and you can use that property to measure temperature. Why? Because in most cases, the increase in volume is proportional to the increase in temperature. So most substances expand when heated, and the increase in volume is very nearly proportional to the change in temperature. Therefore, an increase in volume of a substance can be used to measure temperature, and that is what we do in thermometers. Mercury or alcohol in glass thermometers actually make use of that property. Alright, now here I have a mercury thermometer and an alcohol thermometer, and let me see if I can show. I'm sure most of you have seen thermometers, but let me take a minute to show you these two thermometers. An alcohol thermometer that you see in red and a mercury thermometer on the right. Well, you will see it on the left. So on your left is the mercury thermometer, and on the right is the alcohol thermometer. You can see the alcohol thermometer is much easier to read because you can color alcohol. And this mercury thermometer is very faulty. It has actually broken into pieces. Now, when you supply heat to the bulb of the thermometer, the volume of the mercury or alcohol increases, and you can see the mercury level will rise. And the rise in level can be measured, taken as a direct measure of the temperature. Now see how the level goes up when I dip the thermometer in a beaker of water. You can see the level is going up. The increase in volume is proportional to the increase in temperature, and this is how we will measure temperature. Let's now talk about the different scales of temperature that are in use. What are the common scales of temperature? There are two main scales of temperature for measuring temperature. What are they? On one scale, called the Celsius scale, the arbitrary temperature, namely the temperature at which ice melts at atmospheric pressure, is chosen as its zero. On Celsius scale, 0 degrees Celsius is the temperature at which ice melts. Now, 0 degrees Celsius correspond to the level of mercury or level of alcohol when the bulb is surrounded by melting ice. On the other scale, called Kelvin scale, use a temperature at which the molecular energy is absolutely zero. In other words, the internal energy of the molecules is absolutely zero. If you can reach that state, that will correspond to 0 Kelvin, the Kelvin scale. So, in order to reach that, you got to go down a lot from 0 degrees Celsius. At 0 degrees Celsius, the internal energy of the object is a very high value. In order to reach a stage where the internal energy is 0, or the kinetic energy of vibration or translation of the object is 0, you've got to go way down over here, and that is what we call 0 Kelvin. So 0 Kelvin is the temperature at which the molecules are absolutely at rest. Now, in the Celsius scale, the temperature is measured in a unit called the degree Celsius, and on the Kelvin scale it is measured as Kelvin. Now, this is something sometimes students and even professionals misuse. I have seen bulbs written with maximum temperature 800 degree Kelvin. Now, you don't call Kelvins degrees. When temperature is measured in Celsius, we call it degree Celsius. But when you measure in Kelvin, you will simply call it Kelvin. So can you tell me, 0 degrees Celsius is how many Kelvin? If this is 0 Kelvin, well, I haven't given you the relationship. I will talk to that in a minute. We will use lowercase t to represent temperature in Celsius and uppercase t to represent temperature on Kelvin scale. And the relation between Kelvin temperature in Kelvin and temperature in degrees Celsius is this. T Kelvin is T degrees Celsius plus 273.15. That means from 0 Kelvin, you got to increase the temperature by 273 to reach 0 degrees Celsius. Now, one important thing you must understand is that each interval in Celsius and Kelvin are the same. So that makes it very easy for us to handle. In order to convert Celsius to Kelvin, what all we need to do is add that 273, this difference, and the temperature will then be in Kelvin. 0 degrees Celsius is 273.15 Kelvin. Most of you know this already. So this is 273.15 Kelvin. Now, this is called the lower fixed point of the thermometer. What is the lower fixed point? It's the temperature corresponding to the melting of ice. The temperature corresponding to boiling of water is the upper fixed point. In the Celsius scale, it happens at 100 degrees Celsius. So 100 degrees Celsius is the boiling point of water at normal atmospheric pressure. And what is the corresponding temperature in Kelvin scale? In Kelvin scale, it will be 373.15. So most of these you know already, but keep these things in mind, very important as we go on. All right, mercury in glass thermometer. Let's spend a couple of minutes talking about it. Mercury in glass thermometers are used in the lab very often, and they are marked in degrees Celsius and use the property of expansion of mercury with temperature. I just showed you that. Well, that is an example of mercury in glass thermometer. The length of mercury column in the stem of the thermometer varies linearly with the temperature. You see, because the stem is very narrow, the increase in volume can be considered to be a linear increase. So we can say the length of the mercury column. Now I didn't say volume. You see, the increase in length of the mercury column is proportional to the increase in volume. So I can now measure the increase in length rather than the increase in volume. Now, two fixed points are marked on the stem. I talked about that already. What are the two fixed points? Well, one is called the lower fixed point. Lower fixed point is the temperature corresponding to melting ice. That means you cover the bulb of the thermometer in melting ice, and after the level settles down, make a good mark on the thermometer. That will be your lower fixed point. That will be 0 degrees Celsius. And similarly, if you cover the bulb in boiling water at 1 atmosphere, the level of mercury will increase and settle down somewhere here, and that will be the upper fixed point. The upper fixed point is the temperature corresponding to the boiling point of water. So you got a lower fixed point and an upper fixed point. In a Celsius thermometer, that interval between the lower and upper fixed points are divided into 100 equal parts. Now, if L0 is the length of the mercury column in the stem at 0 degrees Celsius, and L100 is its length at 100 degrees Celsius, and when you want to measure a particular temperature, if LT is the length of the mercury column at that temperature you want to measure, then we have a relationship connecting all those three quantities. Now this is L0, the length of the mercury column at 0 degrees Celsius. This length is L100, that is the length of the mercury column when the bulb is covered by boiling water. And suppose you want to measure the temperature of this water, what you need to do, put the thermometer bulb inside there, and suppose the level of mercury comes here, we will call it L sub T. Now, L0, L100, L sub T are all related, and we can now write a relationship like this. T degrees Celsius, the temperature corresponding to this length is T degrees Celsius, equal to LT minus L0 divided by L100 minus L0 multiplied by 100. That means if you can measure some of these quantities, we can calculate the unknown quantities. Is that right? Alright, let's do a problem using that. The length of a column of mercury in a thermometer is 4 centimeters when it is immersed in ice water, which means this is your L0. And 24 centimeters when the thermometer is immersed in boiling water. This is your L100. What are we supposed to find? What is the length of the mercury column at 22 degrees Celsius? You need to find L sub T. Alright, let's do that. What do we know? We know L0 is 4 centimeters. We know L100 is 24 centimeters. We know the temperature that you want to measure is 22 degrees Celsius. Alright, we want to find the length of the mercury corresponding to that temperature. Alright? Okay, so this is L0, this is L100, and this is the level of mercury corresponding to 22 degrees Celsius. We want to find that length L sub T. Well, what all we need to do is come to our formula. We know T, we know L0, we know L100, we need to find L sub T. I don't think you need my help to do that. What all we need to do is replace all the unknowns by their values, solve for that L sub T. I'm going to leave it for you to solve. I solved it and I got 8.4 centimeters. So at 22 degrees Celsius, the length of the mercury column will be 8.4 centimeter. Let's now look at the B part. If the length of the mercury column is 25.4 centimeter when immersed in a chemical solution, what is the temperature of the solution? Now obviously, if the level has to go above 24, the level of mercury is 25.4 when immersed in the chemical solution. You would expect the temperature to be higher than 100 degrees Celsius. Is that right? Well, we go back to that equation again. We now know L sub T is 25.4. L0 we know, don't we? L100 we know. We can now find the temperature by putting all these values. Our L0 is 4 centimeter, L100 is 24 centimeter, L sub T is 25.4. Bring all those values here, we get that temperature is 107 degrees Celsius. Okay, let's now talk about a different kind of thermometer. There is another kind of thermometer which is called a constant volume gas thermometer. Now very often mercury thermometers are not very useful to measure very small temperatures or very large temperatures. You need some other kind of thermometer. Now, the pressure of a fixed mass of gas enclosed at a constant volume changes linearly with temperature. Now, so far in constructing the mercury thermometer and alcohol thermometer, the property we were using was the increase in volume with temperature. In the same way, if you use a quantity of gas, the pressure of a fixed mass of gas at constant volume, if you keep the gas at a constant volume and then you heat it, its pressure will increase. And the increase in pressure is linear with temperature. Therefore, that increase in pressure can be used to measure the temperature. But remember, you need to keep the gas at a constant volume to do that. That is why we call it constant volume gas thermometer. Now, this is the kind of setup that we will use. This is the bulb that can contain a gas. That can be any gas. You can have air or carbon dioxide. Now, there is a fixed mark here. If you can see the arrow there. Now, the volume, you got to keep the volume a constant. You can see this is an arrangement of mercury. If you remember, in part 1, I talked about a manometer to measure pressure. Do you remember that one? A manometer. It's a U-tube like this. Now, I can change the position of this because this is rubber. Now, by moving it up or down, I can change the level of mercury in the closed tube. You see, this is the open tube and this is the closed tube. Now, when you want to take a measurement, you always bring the level of mercury to this fixed mark. Make sure that the volume of the gas is made a constant. And then you can measure the pressure. How do you measure the pressure? The pressure can be now measured. The pressure at the open end is the atmospheric pressure. So this will be atmospheric pressure plus this H, the difference between the two. So you can actually measure the pressure at any given time, but every time you measure the pressure, make sure that the level of mercury is brought to the fixed mark. Now, the pressure of the gas enclosed in the bulb can be measured by keeping its volume always the same by using this mercury manometer. Now, if you can measure P0, P0 stands for pressure at 0 degrees Celsius. That means cover this bulb with melting ice, adjust the manometer to bring the level of mercury to the fixed mark, and then measure the pressure. That will be P0. When you cover it with boiling water, obviously the volume is going to increase. Now you need to change the position of the manometer to bring the mercury level back to the fixed mark, so as to make sure that the volume is a constant, and then measure the pressure again. That will be P100. And then if you want to measure the temperature of a bath like this, what you need to do is take that bath and insert the bulb inside there and wait for the bulb to acquire that temperature. Then adjust the position of the manometer to bring the level to the fixed mark, measure its pressure, and that will be P sub T. So you know now what is P0, P100 and P sub T. We have a relation connecting all those, just like we had it in the previous case. T degrees Celsius equal to Pt minus P0 over P100 minus P0 multiplied by 100. We can now use this relation to solve problems as we did before. Let's try one. The pressure recorded by a constant volume gas thermometer is 0.4 atmosphere at the ice point and 0.546 atmosphere at the steam point. A. When the pressure is 0.1 atmosphere, what is the temperature? Well, we have P0, we have P100, we have P sub T. We need to find the temperature corresponding to that. Let's write those down. P0 is 0.4 atmosphere. P100 is 0.546 atmosphere. P sub T is 0.1 atmosphere. Well, bring our formula back. T degrees Celsius is PT, P sub T, minus P0 over P sub 100 minus P0 times 100, and use all the known values in there. If you notice, because this is a ratio of two difference in pressures, I can use the pressure in any unit I choose. I don't have to use the absolute unit here. So I can use P0, PT and P100 all in atmospheres. So that will be 0.1 minus 0.4 over 0.546 minus 0.4 multiplied by 100, and that's equal to negative 205.5 degrees Celsius. You see, you can use a thermometer like this, the constant volume thermometer, to measure such a low temperature. Can you use a mercury thermometer to measure that kind of a temperature? No, you cannot. So you can see the advantage of a constant volume thermometer. Alright, B part. What is the pressure at 444.6 degrees Celsius, which is the boiling point of sulfur? Again, you cannot measure these kind of temperatures on a mercury thermometer. Well, again, we have P0, P100, and now the temperature in degrees Celsius. We need to find the pressure corresponding to that temperature. That means we need to find P sub T. So use all the given values and solve for P sub T. Again, I'm going to leave that for you. Apparently I have done it for you. P sub T minus 0.4, this quantity is 0.146, and then cross multiply. 444.6 times 0.146 is this, will be equal to PT minus 0.4, and therefore PT the pressure at that temperature is 1.049 atmosphere. Alright? And that kind of problems are very common and you must be familiar with doing them. Let's set called the triple point temperature. You see, so far we were using two fixed points, that is the ice point and the steam point. Temperature corresponding to melting of ice at atmospheric pressure, that is the lower fixed point called the ice point, and the temperature corresponding to boiling of water at atmospheric pressure. Now, these ice point and steam point are not very easily reproducible all the time because it varies so much with pressure. Now, therefore, a reference point which is more precisely reproducible than the ice point and the steam point is called the triple point of water. Now, what is the triple point of water? Do you know that water can exist as solid, liquid, and vapor all at the same temperature? Have we ever seen that? Triple point is the unique temperature and pressure at which water, water vapor, and ice will coexist in equilibrium. Now, open the freezer compartment of your refrigerator and see how solid ice and vapor water can exist. The vapor will actually fly out of the freezer when you open it. Is that right? The ideal gas temperature scale is defined such that the temperature of the triple point is 273.16 Kelvin. So this is the temperature of the triple point where water exists as water, liquid water, solid ice, and vapor all at the same together. The temperature of any other state is then proportional to the pressure in the constant volume thermometer. You can now use the constant volume thermometer and measure any other temperature because the temperature is then proportional to the pressure measured in the constant volume thermometer. That means if you want to measure the temperature of any object using the constant volume thermometer, you need to take that bath or whatever it is and immerse the bulb that contains the gas inside the bath to measure the temperature. Now, if T, uppercase T, is the Kelvin temperature when the measured pressure is P, then we have a relationship. T equal to 273.16. This is the triple point temperature divided by P3. That is the triple point pressure. That means the pressure measured at this temperature is the triple point pressure. And P corresponds to the measured pressure at this temperature which we want to measure. So look at this. If this is a constant, 273 over P3, then the measured temperature is proportional to the measured pressure. That is the advantage of the constant volume thermometer. So if you know P3 and P, you can calculate the temperature. P3 is the pressure when the thermometer is immersed in a water ice vapor bath at its triple point and is called the triple point pressure. So you can measure P3 by immersing this bulb in a bath that contains water, steam, and ice all at the same time. Let's do a problem. A constant volume gas thermometer has a pressure of 30 torr when it reaches a temperature of 373 Kelvin. A. What is the triple point pressure P3? B. What temperature corresponds to a pressure of 0.175 torr. Well, okay, let's see what are the given things. You are given the measured pressure. We need to find the temperature corresponding to that pressure. T equal to 373 Kelvin. And what is it that we want to find first? What is the triple point pressure? Now, you have been given a temperature and the corresponding pressure we know. When the pressure is P, the temperature is T. We know those two values. And can you therefore find P3? Yes, of course. So, put in the values there. P3 therefore equal to 273 divided by 373 times 30, and that is 21.97 torr is the pressure at that temperature and pressure. How about B part? What temperature corresponds to a pressure of 0.175 torr? So this time you need to find the temperature corresponding to this pressure. We have already calculated the value of P3. So we're going to use that value of P3 in here. We got P, the measured pressure is 0.175 torr. The value of P3 is 21.97 torr. And use our famous equation. T equal to 273.16 over P3 times P. Now take note, the temperature measured using this scale is the Kelvin scale, not the Celsius temperature. So we got the value of P3, we've got the value of P, and using that we get the temperature equal to 2.18 Kelvin. You notice that that is a very, very low temperature. 2.18 Kelvin is the temperature at which the molecules are almost absolutely at rest. Is that right? Okay, we will now use some of these to discuss what I call the gas laws. Research organs in the world. This is the same